So I'm going to start with some motivation. You may wonder why relativistic hydrodynamics, because it describes interesting phenomena for physical systems like neutron-star mergers, black hole accretion disks, or supernovae. It is also relevant in the description of the quark-gluon plasma created in heavy ion collision experiments in VIC or LHC. And it is also relevant in the description, for example, of the early universe, assuming that there is a first-order phase transition, and that this may have proceeded via bubble nucleation and subsequent dynamics, which is potentially detectable by future experiments like LISA. So certainly, relativistic hydrodynamics is interesting for groundbreaking research. But first of all, what is relativistic hydrodynamics? Relativistic hydrodynamics is an effective theory. What is the meaning of that? Let's consider small waves in water. We can describe these waves by considering all the molecules and all the interaction between all these many molecules in a very complicated way. Or instead, replace this very complicated description by a much simpler description provided by hydrodynamics. Or instead, replace this complicated description by the collective description of these molecules, which is provided by fluid dynamics, by hydrodynamics, which is much simpler. Hydrodynamics will be applicable, meaning that it will provide a good description of the microscopic system, in the system of the molecules, if there is a large separation of the scales between the microscopic scale of the system, let's say the mean-free path, and the macroscopic scale, the size of these waves. In the case of a neutron-star merger, we will replace the very complicated description by considering UCD with all the partons and gluons with a hydrodynamic description, with a fluid description, which is much simpler. So from a modern perspective, we can think of hydrodynamics as effective field theory. We perform a gradient expansion, in which the first order, so the leading piece is the zeroth order, the ideal term, and then you can add gradient corrections, first order viscous physics, second order corrections, and so on and so forth. If we think of these gradients as given by this ratio in an intuitive way, this ratio is supposed to be small if hydrodynamics is applicable, and then each term is much smaller than the previous one, in such a way that it makes sense to truncate this series at some given order. We can plug this truncated series into the conservation equation for the stress tensor, obtaining dynamical equations that now we can evolve in time. We can put those equations on a computer and obtain a real-time evolution. Obtaining real-time evolutions is not something optional, but is required if we want to describe all these physical systems of interest. Without these real-time evolutions, we couldn't describe many systems. If we truncate at zero order, then we obtain the equations of ideal hydrodynamics, which are known to be well-posed and have good properties. However, if we truncate the system at first order, then we would obtain what would be the relativistic version of Navier-Stokes, and then, as written in the original books of Landau and Lifshitz, for example, or Eckart, then these formulations, this set of equations present some difficulties. We will review. Now we may wonder, well, is actually viscosity relevant? So do we need to care about the viscous version of these equations? And I will now motivate why we should care about this viscous relativistic system. So in the quark-gluon plasma, viscosity is expected to be relevant because there is a separation of scales, but this separation is not very large. In the microscopic scale, lambda QCD, or the size of the proton, 1 femtometer, and the size of a heavy ion, which is of several femtometers. And actually, this is confirmed by experiments. If you replace the ideal description by a viscous description, you obtain a better description of the experimental data. Now, let's turn to neutron-star mergers. If we first consider black hole mergers, this matter is vanishing, we solve for pure geometry.
Sorry, just a question. I mean, it's not too surprising, no? Because including this matter, you're just including an extra parameter that you can feed for to describe the thing.
Yes, but
so it's not really a.
No, because if you have a system in which ideal hydrodynamics provides an extremely good description, if you add this extra parameter will be compatible with zero. So it's not improving your description. However, in this case, this parameter that you introduce, which is the viscosity, is not compatible with zero. It gives you some value, and with this value, you're fitting better all the data.
Yeah, sure. What I'm saying is that, viscosity doesn't mean that it's because it's a viscous description. It's just that you have an actual parameter to play with.
That helps, of course, because we have an extra parameter, helps in fitting the data, but also the physics includes this parameter. So the physics is included. So it could happen that viscosity is not relevant in a system because ideal hydrodynamics provides a very good description, and viscosity is suppressed, the viscous effects. You include a parameter, and this parameter might be compatible with zero, or does not improve much the results.
That you wanted to say that parameter we can include higher order effects in your physics parameters, while the real value is a bit different. But as you include all the higher order effects in this parameter, you have
in principle, what you really would like to do is to compute the shear viscosity from first principles in QCD, put it in the description, and then find that it actually describes the data. As this computation is very difficult and it's not complete yet, we are fitting this parameter, hoping that we will obtain the same value from first principles. This is the expectation.
Okay.
So it's not just a parameter that you put there and you tune to fit the data, but you also hope that you can compute it from first principles.
And it assumes isotropy.
Yes. So the theory is isotropy, the system, no, because also some physical. Let me now move to the case of neutron-star mergers. Starting from black hole mergers, well, there's no matter here, but in the case of neutron-star mergers, we must specify what is the matter here. And the matter is basically QCD. Is QCD. We have partons, quarks and gluons, and a very complicated dynamics. However, there is a large separation of scales between the microscopic scale, the size of the femtometer, the size of the proton, and the size of the neutron star, which is of the order of kilometers. So we have a separation of scales of almost 20 orders of magnitude. So then, hydrodynamics provides a good description. In particular, ideal hydrodynamics provides a very, very good description because, in this case, from the point of view of QCD, the viscosity is very suppressed, 20 orders of magnitude. So with this, we can solve now the equations of general relativity coupled to ideal hydrodynamics, and this has been done in some detail. And by setting the parameters of, for example, the famous 1708-17 event, then the picture that comes out from the simulations is that we have the spiral phase, they merge in a physically rich post-merger region, which in some tenths of milliseconds, it typically ends up in a black hole. And I would like to focus in this region in which a lot of interesting physics is happening. And if we want to provide an accurate template for example, for the gravitational waves for the future detectors like Einstein telescope, we should include all relevant physics here. We should not forget anything relevant in this region. And in particular, if we study what happens with the weak processes, it turns out that if we compute the decay rates of these processes in this QCD background, we obtain that they operate on time scales which are comparable to the millisecond with the typical scale in this system. And that means that this gives rise to an effective viscosity that we may have to include in the system and take into account. And this has not been explored a lot for the moment, just there are only few works. And there is increasing evidence that this viscosity could be relevant. I will show you what are the works by Retzola in this front. Okay. So also I like to mention that this is a very interesting system in which all the four fundamental forces are playing a role: gravity, the weak force, the strong force, and the electromagnetic force. So it's a very interesting laboratory. Also, to add more motivation, recall that the non-vanishing chemical potential region of the phase diagram remains unexplored, both from the theoretical perspective, from an experimental perspective, for decades now. And now recent experiments like the Bea-Meredith experiment in Greek or other future experiments in Fer or Nita, and neutron-star mergers open two new windows, experimental windows into this non-vanishing chemical potential region of the phase diagram. And in order to access to this region, we need the relativistic hydrodynamic evolutions. And moreover, if we include viscosity, notice that we are dealing with transport coefficients, which typically allow to distinguish more easily between phases. So if we have a phase transition happening here, as for example, the famous critical point conjecture to be in the QCD phase diagram plus a line of first order phase transitions, if we cross this line, maybe the transport properties can allow us to distinguish between the phases. Okay, so I hope I have motivated enough not only relativistic hydrodynamics, but also relativistic viscous hydrodynamics. So the plan is now to present from a historical perspective the relativistic Navier-Stokes equations, present the specific form of the equations, and then I will go on with the real-time evolutions and the applications in these physical systems of interest. So if we consider the original version of relativistic Navier-Stokes as written in Eckart's book or Landau's book, then we find that if written in this form, these equations present severe issues. For example, if we consider a homogeneous thermal state and small perturbations, linear perturbations, these are unstable, they grow exponentially in time, so the system is unstable. So this means that a theory, as the relativistic version of Navier-Stokes, that is meant to describe any quantum field theory in the regime of hydrodynamics, fails completely and would seem to be unphysical. And as a physicist, I would be very worried about this fact. So why is failing this such an important set of equations, and how we fix this? So this question actually surprisingly remained open for many years until very recently. Let me mention that from a modern perspective, we will think going from Eckert equations to Landau equations as a field redefinition. In the context of hydrodynamics, this is called using different frames. But this is from the point of view of effective field theory. This is nothing different from a field definition. I will go back to this later. So now, at some point, I don't know, around 2005 or a little bit later, it was required to consider an evolution that in relativistic hydrodynamics that include viscosity in order to provide a better description of the system. But relativistic Navier-Stokes was not available because it had these severe problems. So what people did in the past was to consider the so-called Muller-Israel-Stewart type theories. These were the first to introduce a novel idea in which, by doing some changes in the equations, in which they extend the gradient expansion up to second order and promote the dissipative part of the stress tensor to be a new variable. They introduce new variables and new equations. They gain some good properties. The problems are alleviated, and this allows to describe the experimental data. So up to some extent, now we have a theory that is doing the job. However, as we will see, still, even if it is able to describe the data up to some good extent, it still has some problems, as we will see, it will relate to this well-posedness. Because at that time, there were no proof of well-posedness for this theory. Actually, there are several variants, like BRSSS, DNMR, and so on and so forth, but I will collectively refer to them as MIS-type theories, as all of them are based on the same idea of adding extra equations and extra variables, while relativistic Navier-Stokes fixes the problems in a completely different way. Okay, so in recent years, so this problem remained unsolved until recent years, in which Benfica Discussion and Goff provided a solution to the problem by computing or by obtaining the well-posedness of relativistic Navier-Stokes equations in a general frame instead of just in the Landau frame or in a specific particular frame. Finding that in a specific subset of frames to which the Landau frame does not belong, then these equations are well behaved, having good properties of well-posedness. Yes, I will comment on that in a second. So for this reason, for these authors, these equations has been known under the name of PD and K, but this just refers to relativistic Navier-Stokes, or in other words, relativistic first-order viscous dynamics. So if you hear about these different things, we are referring to the same thing in principle. Some people like to refer to use relativistic Navier-Stokes only to the Landau's book expression, but according to effective field theory, we should call this also relativistic Navier-Stokes. Okay, so now let me go back to well-posedness and causality. So well-posedness has been well established for many physical relevant equations, like for example, general relativity, Maxwell equations, ideal hydrodynamics, but there are limited results in the context of viscous hydrodynamics, relativistic viscous hydrodynamics. Proofs of well-posedness for Relativistic Navier-Stokes appeared starting from 2017 in different levels of generality, starting from the simplest possible case, like conformal theory, and then extending to the non-conformal case, extending from Gevrey spaces to Sobolev spaces, and so on and so forth. So there were some years of generalizing the results until a point in which the results are sufficiently general that we are now that we can now implement these equations into physical systems of interest. And what they have proven is local well-posedness of the initial value problem, meaning the Cauchy problem, in sufficiently general spaces, like Sobolev spaces, for sufficiently general theories like non-conformal theories and in the presence of charge, like those theories that we need, for example, to describe neutron star measures. Well-posedness, local well-posedness, we call that local existence and uniqueness of solutions. And they also include in these proofs that if they satisfy the conditions that they impose, then also the equation respects the principles of relativity, meaning that there is no faster than light propagation. So no faster than light propagation is ensured, because the characteristics have velocities smaller than the speed of light. And they recall that the characteristics of the PDEs tell you about the speed in which the information propagates. So, as I said, we have sufficiently good properties for implementation in physical systems of interest in state-of-the-art evolution. So now you may be wondering, okay, we have now two theories, the MIS that has been used to describe experimental data successfully for now 20 years, and now this novel theory, which is old in some sense, but has been recently proven to be well posed under some specific subset of frames. So now we can compare these two theories, and we may wonder, why do we need another formulation of viscous dynamics if we already have one that is doing the job? Can we say if one theory is better in some sense than the other? Why, where here better is very ill-defined? Can we define this properly? There are three. I like to put three relevant arguments that are based on well-posedness, on the characteristic velocities not being faster than light, and the ability to propagate strong shock waves. Now, so let me now focus on basically the part of well-posedness, on the argument of well-posedness, but the other two are I could comment on those as well. So well-posedness of the MIS theories were not known until 2020, where Noronian and collaborators constructed the first proofs for a specific subset of MIS theories, in which they obtain some inequalities. I put them here very small because I don't want you to look at them, but there are some inequalities. And the only important point for this that you should know about these inequalities, the most important point, is that they depend on the transport properties and also in the specific energy density and so depend on the state. So you have to check point-wise for every evolution if these inequalities are satisfied, which is quite painful. But in principle, it could happen that they are not violated in any physical system of interest. So let's go and check. And again, Noronian and collaborators check these inequalities in a realistic evolution of a heavy ion collision, finding there are significant violations. Let me make this bigger. So we see here that there are cells. So we can check these inequalities point-wise in space-time, so we can check in which points they are violated, the inequalities do not decide, or they are satisfied. In which there are significant things in which they are violated, or the system do not decide. Now, it turns out that if we take relativistic Navier-Stokes and perform a real-time evolution in a frame in which the system is well posed, this is what we would obtain. Because once we fix the frame, every evolution is now behaving without violating well-posedness. So well-posedness is ensured. Actually, I have already performed these evolutions in a system like this. So I could go to my laptop and show you one of these evolutions, in which well-posedness is essential.
So I don't understand, so this is numerical data. Both
Yes, yes.
on the top and on the
Yes, yes. Well, this is not this is not has not been done yet. So the only simulations that we can have are in my laptop. That I already have them.
We're going to steal it.
I will show you in a second the simulation. But if we are able to perform by construction, they are well posed. So we will see this because.
So my concern is the top one. Why? So if it's violated, is it still okay to do? How can you do numerical simulation?
Okay, good question. So now that there are violations, many things could happen. For example, if there is a lack of well-posedness, the code could crash. We would expect that the code is crashing. So you may wonder what is happening here. Well, in principle, their codes are running. So what could happen is that maybe if you increase the solution, the code crashes. Maybe the code is not convergent in the regions, but they haven't checked. So Noron explicitly told me that they are not checking convergence of the code in the actual evolutions that they use to describe the data. They only check convergence in evolutions of small perturbations around the homogeneous background, which of course is the gradients are much smaller. So it's easy that in that case the convergence properties are satisfied. So many things could happen, and now you may wonder also an important question, which is, well, then are we describing the data properly? Because the data is being described by this evolution. So what is going on here? Well, what probably is happening is that up to some extent we know that this is providing a good description of the experimental data. So if there are some problems, this should correspond to a small deviations that probably are still within the error bars, because there are large error bars in these systems. Because this description is a complicated description of multi-steps, in which there are many steps, and all of them contribute to add some uncertainty. So there are large error bars in this description. So the inequalities are for no, there are different inequalities for each case.
Oh, okay.
Yes, exactly. And for MIS, the inequalities include the energy density, for example, at that point. So you have to check point-wise in a space-time for derivation. However, as I will show in a moment, in the Navier-Stokes case, the inequalities do not depend on the point of space-time. Only depend on the frame that you choose. So once you choose it, then every evolution is well-posed, has good properties of well-posed. Sorry? Different versions.
Yeah, exactly. Is it clear that they're all going to suffer from the same problem as this?
Has not been proven, but intuition says that yes, because they're based on the same idea. And the difference between the different theories is just second-order nonlinear terms. So basically, they will have very similar inequalities, just changing a little bit because of these other different second-order terms that are nonlinear. Actually, it was the inequalities that I have shown are proven only for one specific theory of all the many, and no one has computed yet for the other theories. And actually, if you want to know, well, what would be the result of fixing this problem? The only way of fixing this problem is to consider a different theory in which the problem is absent. For example, relativistic Navier-Stokes. This is the only way that you can now fix this problem here, because if you start with the same initial data, it's impossible to get rid of this, in this theory at least. Okay, so now let me move to neutron star mergers. And as I mentioned, there is only one group performing simulations of neutron star mergers, which includes viscosity. They include bulk viscosity, and this has been performed by Zavalov and Barcelona. And it turns out that they use MIS, because this is the standard tool for including viscosity in relativistic dynamics. So they use MIS theory, and then again they suffer the same issues. They find regions in which these inequalities are violated. So what they do is by hand, in those regions, they change the parameters. For example, the bulk viscosity is constant everywhere, but in those regions, they change the bulk viscosity in such a way that you avoid violating the inequalities in order to have some simulations.
No, I don't understand that part. So is that causing issues in the evolutions then?
Probably yes, because what they do in practice is to avoid these regions by changing hand in those regions in such a way that you skip this violations. So they have to change this by hand. This, I think that they don't mention how large this region is. They mention that there are some regions in which they have to change by hand the parameters in order to not violate those inequalities. No, it's just to keep well-posedness. Okay, so if we implement now relativistic Navier-Stokes, we ensure that well-posedness is satisfied. So if we were able to perform a neutron star merger by using relativistic Navier-Stokes, then we wouldn't have these problems. So now we can try to perform this implementation. And this, then, in this sense, relativistic Navier-Stokes is a promising alternative to it. So I have shown you specific examples in which these inequalities are violated, and so well-posedness is not ensured. But even if in all current simulations these inequalities would have been satisfied, we still would have to check these inequalities in every future evolution. However, if we use relativistic Navier-Stokes, this is satisfied for every evolution that we perform. So in this sense, at a fundamental level, then Navier-Stokes is a promising alternative to MIS in which we do not have to perform these checks in every evolution that we perform. So in this specific sense, I would say that the theory is better at a fundamental level. Okay, so if you don't have questions, we can move to the question. It's comparable. It depends on the specific case, the dimensionality, for example, but yeah, it's comparable.
So I suppose you were going into this in more detail now, but I'm wondering, like, at this level, like, what drawbacks does the relativistic Navier-Stokes have with respect to?
What are the details?
Well, like, what is the price to pay to have well-posedness?
What is the price to pay to?
Yeah, no, maybe I can answer at the end.
Okay, I will explain now specifically how they fix the problem, so maybe that helps in asking. Okay, so let me present the equations. I will consider the conformal fluid because of simplicity, but everything extends naturally to more general cases. But for presentation purposes, this is it. Let me start by ideal hydrogen. As I said at the beginning, the equations are well posed. A good problem. But if you consider first order hydro as written in Landau's book, then we have some problems. Now let me start from this expression and consider, instead of effective field theory, the most general field definition. Actually, this is a perturbative field definition, which is first order terms. The most general first order terms compatible with the symmetries, with Poincare symmetry and with conformal symmetry. And they have some specific form. But now, if we perform this field definition here, we obtain the most general, the extension of first order viscous dynamics in the most general frame. What is the meaning of having different frames? Well, we have here two real numbers, which are two constants, that specify the frame. We choose this to be 4 and 4, and this is one frame, 5 and 5 is another frame. If we choose them, 0 and 0 will be covered another. So they are arbitrary. So now the insight by these people was to realize, so this was basically well known, that there are many different frames. Actually, even in the original books, there are different frames in the different formulations by Yago now lived. This is not a novel thing.
One question, do these constants A1, A2 have to be constants, or can they depend on the zero-order backgrounds?
No, they have to be constants. Once, actually, we put the dependence on energy here in the eta, so we choose that they proportional to eta in such a way that now the only freedom is a constant.
Okay.
And this is this is fixed by conformality. How it depends on energy is fixed by conformality.
Okay, but that's only applicable to the conformal theory.
Yes, in the non-conformal case, what you have is, instead of a number, a function. So you have more freedom. Okay. But in principle, you can proceed. There is no problem. You have more possibilities. Okay, so this was known, and the novelty by these people was to perform the analysis of well-posedness in this general case, not just in this case. to find that if we are within this specific subset of frames, then the equations have good properties. And notice that the Landau frame is not within this frame, and there's a gap between them. Okay, so now you might be wondering, well, I am used to think in these terms. So what is the meaning now of this other term here? Basically, is A and Q. What is the physical meaning of these terms? Well, let me notice something important, which is that these terms are precisely the ideal equations of motion. We decompose this into this transverse and longitudinal to velocity. We have the same expression. So they are proportional to the lowest order equation of motion. That means that on shell, they are of higher order. If you use the equations of motion, you can push these expressions to higher orders. But here we have decided to keep them. Because if we keep them, we have good properties. And moreover, as they are of higher order on shell, they should not affect the physics. So the physics is not modified. The physical predictions by these equations should be the same, according to effective field theory. Actually, you might be wondering, well, but I am used to be told that when I change from Eka to Landau frame, I change the physical meaning of the velocity. Yes, this is true, because here, in the change of frame, the term is not proportional to the equation of motion. We can distinguish two types. The ones that are not proportional to the equation of motion, like Eka to Landau, and this other type are proportional to the equation of motion. And then they do not change the physics. And now this is the fact that they do not modify the physics is a formal statement in which we assume that the gradients are infinitesimally small, and so each term is completely negligible with respect to the previous one. But in a real-time evolution, gradients are not infinitesimal, they are finite. We have to decide or to establish criteria by which we decide when one specific term is negligible and when the physics to first order is invariant. Because we can have a continuum from being very deep in the regime of hydrodynamics to be very far away from equilibrium. And with the real-time evolutions that I will show in what follows, I will consider also specific criteria by which we can make this precise. But before going to that, let me consider a couple of comments. First, one comment in quantum field theory, which is, well, first a comment in general effective field theory, which is that in effective field theory, there's a general statement that tells you that when you have a term proportional to equations of motion, then you can push it to higher orders by using the equations of motion, when this term is proportional to the lowest order equation. So this is a general statement that applies in particular, for example, in the context of quantum field theory. Consider chiral effective theory, and you find terms that are proportional to the lowest order equations of motion, you can remove these terms. These are called, in that context, redundant terms. And the usual statement is that the S matrix remains invariant. Now, in the context of gravity, these ideas have already been applied to the context of gravity. We know that in the context of gravity, we can consider effective field theory, like thinking in a quantum theory of gravity expressed as a general relativity plus small corrections. And then we truncate the series, assuming that these corrections are small. And then we know that typically these theories have bad properties of well-posedness. It's quite difficult to obtain well-posedness in these theories. By using this idea, Paul Figueras, which is my collaborator, considered this same kind of terms in this context of gravity. And with these terms, you can recover well-posedness by using basically the same idea. You introduce terms that are proportional to the lowest order equations of motion or lower order. These terms do not affect the physics, so the predictions of the theory should be the same if you are in the regime of effective theory. But they regulate the equations in such a way that now the principal part of the equations, which is the important part for well-posedness, changes in such a way that now the equations are well-posed. And with this, you can regulate a lot of high derivative theories. Okay. So let me then move to the evolutions. So first of all, I have been talking about mathematical results of relativistic Navier-Stokes, but for the moment, we haven't shown any any solution. So do these equations admit solutions? So these are all the works up to today in which real-time evolutions of these equations has been performed at a nonlinear level. And the first important evolution is that they admit physically sensible solutions. For example, we have studied sound waves or the Riemann problem, shock waves, and other standard solutions to the dynamic equations, finding that the solutions are physically sensible. For example, yes, typically, for the moment, only in Minkowski, yes. No one has obtained solutions with these equations in other background different than Minkowski. So for the moment, there is no gravity or any gravity background different than Minkowski. Okay, so now an important question that I would like to address, because we want now to implement these equations. We are at the level of trying to implement these equations in physical systems of interest. But we have the possibility of choosing different frames among these. Within this set, we have many possibilities. So is the physics actually invariant if we change frame here? So this is what I want to check now and to provide specific criteria. Actually, this specific criteria would be applicable also in these theories of gravity that I have mentioned. So for this, with this criteria that I will define this statement actually and provide evidence for it, which is that the arbitrarily chosen frame, this frame, does not affect the physics up to first order. I have to define what do I mean by that, as long as the system is in the effective field theory regime, which typically we mean that each term is much smaller than the previous one in this gradient expansion. For this, I will define three criteria. Basically, the first criteria is that the solution is within the effective field theory regime, meaning that each term is much smaller than the previous one. If this is satisfied, let's say within a 10%, we have to put some specific quantitative criteria, but this is the intuitive criteria. Then we say that the solution is in the effective field theory. We have a specific quantitative criteria using norms and specific percents, but this is the use. Notice, so now one of you might be wondering, well, but if I am solving the equations of relativistic hydrodynamics, then the solution is in the regime of hydrodynamics because this is hydrodynamics. And the answer is no, in the following sense. These are equations that I obtained by truncating the series, plugging in the conservation equations. I have some equations, but the truncation has been performed. And now I can put any initial data that I want, having arbitrarily strong gradients in such a way that the solution will be arbitrarily far from equilibrium. So what I need to do in order to check if the solution is within the effective equilibrium or not, is to check that if this is satisfied in the solution. Something that because I went to several talks about extended theories of gravity, in which they consider general relativity plus a small correction of a new term, higher derivative term, and they perform the evolution, and they say, well, as the coefficient here is small, then we are in the effective field theory. And this is not correct, because you have to check if this is satisfied or not in the actual solution. And this is typically something that I haven't seen in those talks. Okay, so now that we can consider criterion B, which will tell us about the fact that these terms are not affecting the physics of first order. So what I'm comparing here is the field definition dependent terms, the terms that are proportional to these constants, and the actual first order viscous term. And if they are actually second or higher order, they should be much smaller than this term. In such a way that if I multiply this term by a factor of 2, that I can do because I can just multiply this, I can choose another frame, which is a factor of 2 different from the other one, then this term should be still much smaller than the previous one. Shouldn't affect, and in this sense, they do not affect the physics to first order.
One question. So earlier you had this example of the conformal theory where you had the two coefficients and you had a lower bound of them based on well-posedness. Does this criterion then impose an upper bound, perhaps, on those coefficients?
Yes, this is a good question. If we have an upper bound. Well, the answer would be yes, because if you keep increasing these parameters forever, at some point, you will make this larger than this, actually. So, in principle, yes. You should use, actually, one of the conclusions of doing many simulations is that it is interesting in practice to use values that are close to saturated inequalities. Actually, to use values that actually saturate the inequalities is the one of the best options for several reasons. One of them is that one. But you could increase the numbers such a way that this is bigger than this. But there are other reasons.
You mentioned modified theories of value. I think most of the community doesn't look at it as an effective description. They look at it as a theory per se, and therefore you're allowed to have. Okay, but suppose I have, so that criteria,
This one.
would tell me then that even when I include first or second order terms, I always need to be within the ideal approximation, the ideal ideal to a very good level. Is this excluding any, for instance, viscosity driven instability? Suppose I have, they are known, by the way. Suppose I have some system that's driven and stable by the viscous term. Would you forbid this from happening?
With arbitrarily small viscous term?
Yeah.
Well, then you will not see it in the if you evolve the ideal equations. Probably.
Yes, you will not. But these are known to exist.
Yes, but if they exist, then well, what would happen is that ideal hydro not capturing it. If you evolve viscous hydro, in principle, you should be able to see it. And
But you would say I don't trust it.
no, you will say that you perform the evolution, and you will see that there is some instability. The unstable terms grow,
Yeah.
And at some point it will be violated. But at the beginning of the evolution, if they are very small, this is satisfied. So you can check this point-wise in space-time to see where you start to violate them. Okay, so we can now apply this to specific cases. If I consider a homogeneous thermal state, I can touch it, and then the fluid moves a little bit. Then we have a sound wave, and if the wavelength is very large, then it's by construction the renewal dynamics. So actually, when these are the same expressions, if we now consider the pxx component of this extension, for example, at the center, and then we plot the different quantities, the different so in black we have the ideal part, in blue the first order, this is second order, so we see that there is a clear hierarchy between them. And also there is a clear hierarchy between these terms that are in red here and the blue one. So this is satisfied as expected because we are in the range of dynamics. Now we can perform many evolutions in many different systems, from shock waves to Gaussian perturbations of large amplitude in many other systems. And by analyzing a variety of solutions, we conclude that if criterion A is satisfied, then criterion B is satisfied. So with this, we can say that this statement that I proposed before, that if the system is in the range of dynamics, effective field theory, then the system to first order, the physics to first order is invariant under the change of frame is satisfied. We think by defining this criteria. Without the criteria, other things could happen. But of course, one must define one criteria, one want to answer this question. Now, again, I can, once we have, let's say, shown this, we can again say that these novel terms can be thought as a mere regulators, and the physics is left invariant. Because we can think of the energy density as in the usual Landau frame. But the physical meaning of the variables is exactly the same. And this is quite good because now people, we want to implement this, will already understand what is the meaning of the variables. There are only just some terms that you can think as regulator if you want. So to make the equations well posed. Okay, now I will define a third criteria, which I think is also very useful, because even if these terms are small locally, point-wise in space-time, it could happen that they accumulate on time because these are non-linear equations. So we must be careful. So in the criterion C, what I will consider is two evolutions in different frames, and now a third evolution in ideal hydro. In such a way that now I can compare the difference between the two evolutions in two different frames, and this should be much smaller than the difference between one of these evolutions and the ideal evolution. Because the ideal evolution and the viscous evolution is different by the viscous terms, precisely, and the other two are different by second order terms. And this, by defining this, so I can perform the two evolutions of different frames, for example, separated by a factor of 2. I find that the two evolutions are very close to each other, with the field definition dependent terms, which are the red ones, different, but the other are very, very similar to each other. These are different as expected because they are multiplied by a factor of 2. And now, if I first,
How will be distributed in space?
in this case, what I have is a sound wave. So this is Minkowski. This is a homogeneous thermal state.
It's 3 dimensional.
No, the fluid is 3 + 1 dimensional, the fluid, the theory, but the system is just 1 + 1 planar symmetry. So the other, so this is X direction, but the other two, the Y and Z, are completely homogeneous.
Okay,
So this is planar symmetry. Yes, it's effectively the dynamics is 1 + 1. But for studying these aspects in principle in general, and my intuition is that all this will naturally extend to dynamics in 2 + 1 or maybe 3 + 1.
It's infinite.
Yes, in this case, well, with periodic boundary conditions, so it's in some way. So, well, if I do this comparison that I told you, which is comparing the ideal to one of the viscous, any of the viscous and the viscous between themselves, then this difference will be much smaller than this, precisely as we want, because, well, this, and this is under a real-time evolution, so comparing these 3 real-time evolutions. So this captures, in some sense, a global aspect of the evolution. So, and this criterion is complementary to the criterion B. So now, after analyzing a variety of solutions, we can conclude that criterion B is satisfied, A is satisfied, B and C are also satisfied. And with this, we have more different criteria to assess this statement. Okay, so maybe. Okay, and then motivated by the physics of the quark-gluon plasma, we can consider systems which are marginally in the regime of hydrodynamics, meaning that first order terms are not much smaller than zero order terms, and so on, and see if the physics is still invariant to first order. Because in heavy ion collisions, precisely, this situation happens. There are situations, or in many of these situations, gradients are not very small at the beginning of the simulation when the code is initialized. So for this purpose, we analyze situations that are marginally in the regime of dynamics, and then we find that the criteria are robust, meaning that if criterion A is only marginally satisfied, criterion C is still satisfied. Criterion B is also marginally satisfied, but C is still satisfied. So with this, we are also making sure that we can still apply this in the context of heavy ion collisions because it is satisfying this good property also, even if gradients are not very small. Okay, I will skip the initial data and I will comment now on applications, on the 2 applications that I already commented, which is in quark-gluon plasma and neutron star measures. In the context of the quark-gluon plasma, we have seen that there are limitations, we have seen explicit examples, and now we also know that in the Navier-Stokes description, if we were able to perform this evolution, this would look like this. Because once we choose the frame within this specific set of frames, well-posedness is active. And now we also have control on the frame dependence and on the initial data, actually, and all the details, so we can proceed with implementation. So the most natural step to start with this implementation is to consider the radial flows in central collisions. We consider central collision of heavy ions. Then there is a radial expansion, which is axially symmetric. So effectively, if we consider boost invariance in the other direction, we have physics happening, the dynamics is happening 1 + 1. So it's the easiest case. So this is one of my simulations. I have constructed here a code in Mathematica in which I evolve the Relativistic Navier-Stokes in a non-conformal case with an equation of state and transport parameters obtained from the ones that I use in QCD. And with this, I can try now to fit the data. This is actual data. This is the lots. This is for pions, kaons, and protons. And with these simulations, I can now fit this data, providing the first fits to data by using relativistic Navier-Stokes as a proof of principle that relativistic Navier-Stokes can do this job. And now, regarding neutron star mergers, I found that there are limitations. We call that they are fixing by hand some parameters in order to keep having a well-posedness.
So one question for the previous slide. You said that in QCD, the transport coefficients haven't yet been calculated from first principles. But then you said that in your simulation you were using transport.
Good question. So the transport coefficients that I am using are the ones that are obtained from fitting to the data, in which there are large error bars, order 1 almost, but you have some values.
So in a sense, you're going through your simulations and fitting the coefficients, judging by which ones fit the data best.
Yes, yes. So I'm in that sense, I'm using the coefficients that have been used, having obtained by fitting the data using MIS.
Okay.
But this is as a proof of principle.
But shouldn't you obtain the coefficients?
Indeed. But this is in a second step. I will do this in the future. But for the moment, just as a proof of principle that these equations are able to describe the data, I will use these coefficients. And then, actually, this is a very simplified scenario. I consider very simple initial data. I'm considering the particularization step, in which, well, the freeze-out step is also in a very simplified setup. But I think that this is enough for providing the first steps in this direction. And then you can, let's say, include all the details. Yes. So in the case of neutron-star mergers, now we have control of the numerical evolutions, so we can perform the first steps in the direction of constructing neutron-star mergers by using relativistic Navier-Stokes. And actually, we are already performing this. We are performing the triple decomposition of the equations, and with this, we can now perform the next step, which is to perform the first step, testing spherical symmetry to see that everything is going well, and then finally implement this in the 3+1 code. And we're doing this with Pau Figueras and the other people in Mallorca and Nottingham. So with this, we expect to obtain accurate templates, which include all the relevant physics, including the viscosity, and so this will be relevant for the future experiments like the Einstein telescope, where this post-merger region of the neutron-star mergers is expected to be detected. Okay, so let me summarize then. So I have explained that in the historical first formulation of the relativistic Navier-Stokes equation, there were some problems, as written in Landau's book. Exploring remained open for many years. Meanwhile, MIS theories were used to discover the data. Up to a large extent, they are doing very well to discover the data, but still they present some limitations at a fundamental level, meaning well-posedness, that we have shown in specific examples, both in UCD and quark-gluon. And in relativistic Navier-Stokes, these problems are absent, long as we choose a good frame. Our studies of real-time evolutions conclude that we define and provide evidence for the statement that the arbitrarily chosen frame does not affect the physics to first order, as long as we are in effective regime. And we can think of these new terms as regularizing the equations while keeping the physics the same. So the predictions of these equations should be the same. And we control the initial data. So we are ready to implement this relativistic Navier-Stokes equations into these physical systems of interest, like the quark-gluon plasma or the neutron-star mergers. Okay, thank you.
Thank you very much. Questions?
So all the apply to viscosity space, but you're able to get results for the Einstein telescope to meet the quantum shocks right?
Well, gravity coupled to fluid dynamics. They're coupled, so but
yeah, so you need to now what you need to use the curve space time.
yes. And we're starting this program.
Okay.
And the proofs of well-posedness are also for the for hydrodynamics coupled to GR. So are not only for Minkowski. So in principle, the proofs also apply to this other case.
Questions?
Sure.
So now that it's been are there any disadvantages of relativistic Navier-Stokes as compared to the main theories?
Are there advantages in which
Any disadvantages?
disadvantages? This is a good point. So the main disadvantage that I usually like to say is that all the infrastructure for MIS has been constructed, so it's available, and we just have to go there and use it. For example, if you go to, the codes that are used in heavy ion collisions are available. You can go there and check the details. But this has not been constructed for relativistic Navier-Stokes. In this sense, this is one of the disadvantages. And in other aspects, well, for the moment, I would say this is the main disadvantage. But Well, it's just a matter of constructing the new infrastructure for these new equations.
Questions?
Well, it's like two because I don't know the answer to the first one. It depends, but like would viscosity so you had shocks in the ideal hydrodynamics case. Would viscosity smoothen them?
Yes, they're smooth.
Okay, yeah, that's what I guess. So the question is like, what happens in those cases where you want to compare, say, ideal hydrodynamics to viscous hydrodynamics when you have these kind of terms where one develops shocks and the other?
Yeah, this is a very good question. Actually, I have addressed this question already, and because I have a section of shock waves in this paper, for example, and then I have to change the criterion C, in which I perform an evolution in ideal hydro, because well, in that case you cannot compare point-wise because well, you have discontinuity.
Okay.
But well, you can do other kind of comparisons. Yeah, you are completely right.
I wanted to ask something. So, in the first point of your conclusions, you said that the results seem to be independent of the particular frame chosen as long as well-posedness is satisfied. That's a bit puzzling to me because if you choose the coefficients differently, surely the dynamics would slightly change, right?
Yeah, slightly, yes.
But
So this is why it is important to say up to first order. So this is why I say here up to first order, because the slight difference are contained in the second order or higher. So they are similar, but they are so one solution is not mapped to one solution. It's mapped to one solution plus small corrections due to higher order terms. So there are small differences.
Somehow within the range where the effective field theory is valid to first order, the possible choices of transport coefficients, the difference between them only gives you corrections up to the next order?
Yes, which are small if you are in the regime of effective field theory. So this is why it's important to be in the regime of effective field theory in such a way that higher order terms are smaller, and then you can neglect these second or higher order terms.
We think of a system of physical relevance where we want to be clearly outside of things of the effective field.
Yes, you can construct it whatever system you want. For example, a strong shockwave, or if you put a Gaussian which is very sharp, this is already away from the regime of dynamics. Or in an actual evolution to describe the quark-gluon plasma, when you initialize the code in the first femtometers over C, there are some, well, you are slightly away from the regime of dynamics. So yeah, but it's just a matter of choosing initial data that is sufficiently far away from equilibrium, meaning having large gradients.
Okay. Questions? It's
I'm going to speak about the relationship between your political criteria, when you say that such a quantity has to be much bigger than another, and the choice of the coordinate basis.
Okay.
So to what extent is there an invariance here, right?
Okay.
What do you measure?
This is not covariant.
Yeah.
This is not covariant. So we should find a covariant version of this.
Yeah.
One way in which I'm thinking of this is to take T mu of the ideal part plus T mu of the first.
And then say that needs to be, but still that's not possibly definite, right? Because you're raising the indices with an object, it's not possibly definite.
Yes. Okay.
So it's not going to find a
Yes. Actually, no one has thought about this point, and this is important in shockwaves, for example, because in shockwaves, if you are in the frame of the shockwave or you are on the lab frame, this is completely different. The applicability of hydrogen is completely different. So one must define something which is covariant, something of that kind. But this has not been defined in the literature as far as I know. But it's actually an important point to provide a covariant definition of what I explained of criterion A and B and C.
If you enjoyed the video, like and subscribe.